Hello and welcome to day 2, some more normal curve today. I'm not going to go over any of the homework questions. Most of you seem to get it totally fine. If you do have questions, I will answer them individually. But let's start with this warm-up. So you took the SATs and the ACTs. You scored an 1140 on the SAT and a 25 on the ACT. You're having a hard time deciding which score you should send to the colleges you're applying to. You only want to send the best score. The mean SAT score is 1,000 with a standard deviation of 100, and the mean ACT score is 20.8 with a standard deviation of 4.8. Which score should you send to the colleges? So here's a good example of when z-scores are helpful. You've got two different measures, two different metrics that measure the same thing, your success in college. And you want to know which of the two is technically a better score. So if you normalize both with the z-scores, you can compare them that way. So find the two z-scores and tell me which one you should send to your college. All right, you ready to see the answer? Okay. So remember that if you're finding a z-score, you're doing the observed value minus the mean divided by the standard deviation. That's the formula we learned yesterday. So for the SAT, your z-score would be your observed score, which is 1140, minus the mean, and the mean on the SAT was 1,000, divided by the standard deviation, and it said the SAT has standard deviation of 100. So if you do that, we can figure out what our z-score is. Let's see. 1 second, let me grab the calculator here. All right, here we go. So it'd be 1140 minus 1,000 divided by 100. Oops, and that's a terrible way to put it in, sorry. Use alpha y equals, or hit enter when you do the top. Let's try that again. 1140 minus 1,000 divided by the standard deviation of 100, and you get 7/5, but I'd rather make that as a decimal, so you can actually do math decimal also. It's 1.4. Okay, so the SAT has a z-score of 1.4. Let's do the same with ACT now. So for the ACT, our observed value was 25, because that's what we got on there. So z equals 25 minus the mean was 20.8 divided by a standard deviation of 4.8. And I can use alpha y equals again. 25 minus 20.8 divided by 4.8. 0.875. So which is the better score that you should send to the colleges? Yeah, your SAT. Because remember what a z-score does. If you think of a normal curve, and both SATs and ACTs would follow normal distribution, the mean is in the center. So my ACT score of 0.875 would be there, whereas my SAT score of 1.4 would be up here, which means SAT scored higher. So the SAT is the better score to send. You're more standard deviations above the mean, which means you did better than more people. Your random fact of the day: every ton of recycled paper saves about 17 trees. Make trees happy. Okay, today we are doing more with the normal curve. You're gonna need your calculator for sure. And we're doing this thing called probabilities and percentiles using the normal curve. So some of this is gonna seem like review, and then I'm gonna go a little bit further. It says Kevin's math grades are steadily improving. Good job, Kevin. His test average is now an 88. The mean of all students' test scores in the class is a 91 with a standard deviation of 3. Assume test scores in this class follow a normal distribution. Calculate Kevin's z-score. Okay, so z-score, like we just did. What's the observed value here? It'd be 88, his specific score, minus the mean, which is 91 right there, divided by the standard deviation, which is 3 right there. And if I calculate that, I'll get his z-score, which I can do it in my head. 88 minus 91 is negative 3. Divided by 3, his z-score is negative 1. Does the z-score suggest that Kevin did better or worse than the average math student in his class? Justify. What do you think? If his z-score is negative, did he do better or worse than the average? It's worse because a negative z-score is to the left of the average. So even though it's improving, he's still a little bit below average, which you could see just by knowing that 88 is below 91. So it's worse. His z-score is negative, which means it is below the mean score. Okay. Part C, on the normal curve below, label the mean and standard deviations of the class scores and put a star at Kevin's score. Okay, so where does the mean always fall on a normal curve? It falls at 0. So the mean would be here. And that would be 91. And what did it say the standard deviation was? 3. So that means that between 0 and negative 1, the standard deviation is a distance of 3. Because remember, these numbers on the bottom mean the number of standard deviations away. This is half a standard deviation. This is 1 standard deviation, 1.5. Those are all below. These are all above. So that's standard deviation. So knowing that, where would Kevin's score be? All right, well, his z-score was negative 1. So there's 2 ways to do it. We know he should be here. There's his score. But it should also make sense that if you subtract 3 from 91, and go 1 standard deviation below, you get his score of 88. So like what would this score be up here? This would be 94. And then this would be 97 because I'm going up by 3 every time. Just like I'm going down by 3 every time. Make sense? Good. What percentage of students are doing better than Kevin? Okay, well, think on this curve. And I should mention, nowhere in here does it say that this is a normal. Oh, it does. Okay, assume test scores follow normal distribution. Good. I can't use this graph unless those words are in here, where it says assume test scores follow a normal distribution. That lets you use this graph. So what percentage of students are doing better than Kevin? So think about what this would look like. Here's my normal curve. We just figured out that Kevin was at negative 1. And if I'm doing better than him, that means I'm over here. So if I want to know what percentage of students are doing better, this means to add all percents above negative 1. So all of these get added. So 15, 19.1, 19.1, all the way through. So 15 plus 19.1 plus 19.1 plus 15 plus 9.2 plus 4.4 plus 1.7 plus 0.5 plus 0.1. All right, so maybe slightly tedious, but we can type that all in the calculator. So 15 plus 19.1 plus 19.1 plus 15 plus 9.2 plus 4.4 plus 1.7 plus 0.5 plus 0.1. I do all of that and I get 84.1%. So about 84.1% of the people are still doing better than Kevin. Now, you know an easier way to do that? What do you think all the percentages from 0 to the end would be? If I take this half of it, what should all of this add up to if it would make sense? Yeah, 50. half of this is 50%, half of this is 50%. This should all be 100% of the data. So if I do 50% plus, what's this, 24 point or 34.1, that's where 84.1 comes from. Kevin is doing better than what percentage of students? So this is slightly different. If Kevin, whoever Kevin is doing better, that means that here's Kevin here. He's doing better than all these people. So here we're going to add all percent below -1. Okay, so that would be 0.1 plus 0.5 plus 1.7 plus 4.4 plus 9.2. And then I'm at 1. I just looked at all these numbers right here. That's where this came from. Okay, so a little bit easier to add up. 0.1 plus 0.5 plus 1.7 plus 4.4 plus 9.2. And I get 15.9%. Anyone come up with a faster way to do that? Well, if I knew this whole side was 84.1, I could get the leftovers by subtracting from 100%. So if I did 100 minus 84.1, we'll also get 15.9. Kind of like a complement idea from probability. All right, finally it says shade the area to the left of Kevin's grade of an 88. The sum of all the shaded areas is called a percentile. Okay, so this is a new vocab word that you're going to see come up, and I'll write it again on the next page. Mean was at 0, z-score of -1. Whenever you do at or below, that's also the percentile. So this is telling us that Kevin's grade is at the 15.9th percentile. Okay, so when you see percentile, that means that that percent of the people did worse than you. So you did better than about 16% of the people. Kevin did better than about 16% of the people. Okay, so let's go to the next page and rewrite the definition of percentile. Percentile is just the percent of data values that fall at or below a given data value. Okay, and I stress at or below. When you hear the word percentile, you want to think at or below. That'll help you. Now, where you most often see percentiles is you'll get them in your score reports for SATs and ACTs and big college tests like that. So if you haven't seen those already, you will pretty shortly probably, but your score report will always tell you your percentile. And you want to be at a higher percentile because that means you did better than that percent of the people. If you're at the 10 percentile, then you only did better than 10% of the people. Most people did better than you. But if you're at like the 98th percentile, you scored better than 98% of the people taking the test. That's a pretty good measure. Okay, so here's number 2. You took the SATs and did not receive your numeric score for the math portion. Testing service only stated that you scored at the 97.7th percentile. Is that good? Yup, that means you scored better than almost 98% of the people. The mean score is 525 with a standard deviation of 100, and SAT scores follow a normal distribution. What score did you receive? Okay, well, here's this chart again. What score would go here? Whatever the mean is. And it says the mean score is 525. So this is 525. It wants to know what score did you get if you were at the 97.7th percentile. So I got to figure out where 97.7, where that percentile falls. I don't have a z-score that I can find. So the only way to figure out where 97.7 is to add up all these numbers until I get to 97.7. So remember what this means. When I see 97.7 percentile, this means 97.7% of test takers scored at or below your score. So that's pretty good. So if I want to figure out what score I received, I have to find out where I am on the chart. So we need to add percents. Until you get to 97.7. Okay. Well, I could start at 0.1 plus 0.5 plus 1.7 and start adding, or I could say, well, I know I'm more than 50%. So if I take all of this to here, how much is that going to be? That's going to be 50. Then start adding on. If I add on 19.1, that's not going to be enough yet. 69.1. So go further, add 15. 84.1, still not enough. So go further, add 9.2. 93.3. I gotta get to 97.7, so add 4.4. There it is, 97.7. So I had to add everything up until I got to the 4.4. So right to here, that was 97.7. So all of this equals 97.7%. Some of you might be thinking of an easier way to do it. Since this is so close to 100, I could also just do 100, start from this end, minus 0.1, minus 0.5, minus 1.7. You'd also end here. So either way, totally fine. Okay, so this is where I'm ending. Now, what does the question want to know? What score did you receive? So what's the standard deviation? It's 100. So that means that if the standard deviation is 100, that distance here equals 100. Okay, so this would be 625. Add another standard deviation of 100, I get 725. So that must be my score. So you scored a 725. Now, this fell at a nice spot. Let me show you one other way to do it. You could also say, okay, I know that I'm at 2, so I have to take the mean plus 2 standard deviations. The mean was 525 plus 2 standard deviations. That's going to get me this number also. So if you'd rather kind of almost make a formula out of it, 525 plus 200, you can get it that way also. So if counting is hard for you, especially if it's like a 0.5 or something, you might want to use that. Okay, it says your friend is really bad at math. She was in the 6.7th percentile. What score did she receive? Okay, so now I need to figure out where 6.7 falls. So same thing, start at the left. 0.1 plus 0.5 obviously isn't going to be enough. Plus 1.7, still not enough. Plus 4.4. Nope, there's 6.7. Okay, so we added up 0.1, 0.5, 1.7, 4.4. This is where I ended. So this part right here, 0.1 plus 0.5 plus 1.7 plus 4.4. That got me to the 6.7 because remember percentile means at or below, so I started below until I got to 6.7. So this tells me I'm at negative 1.5 standard deviations. So if I take what I did up here and say I need to take the mean minus 1.5 standard deviations, that would be 525 minus 1.5 times 100. And I get 525 minus 1.5 times 100. And my friend only got 375 on the math SAT. Okay, or you could count. 525 minus 1 would be 425 minus a half deviation. A half deviation would be 50, so 425 minus 50 gets you the 375. Make sense? Hope so. Okay, number 3. The average number of shoes in a girl's closet is 6.5 with a standard deviation of 1. Assume this is a normal distribution. What percentile is Mrs. Crowfoot in if she has 5 shoes in her closet? So always draw a picture. And what's going to be in the middle? The mean, which is 6.5. Mrs. Crowfoot has 5 shoes in her closet, so we got to find out where 5 lands. So what would be at minus 1? Well, since standard deviation is 1, subtract 1 from 6.5, you get 5.5. If I subtracted another standard deviation, so if I went to negative 2, I'd be at 4.5. So that means where is Mrs. Crowfoot if she has 5 shoes? Right here. So 5 shoes is at negative 1.5 standard deviations. Okay, then you got to remember you're looking for the percentile. What's percentile mean? What phrase are you supposed to think of? At or below. So you want to add all the percents below negative 1.5. So we're going to add percents below negative 1.5. So let's look up at this chart again. Here's negative 1.5. It's the same one I just did. 4.4, 1.7, 0.5, and 0.1. You know that's going to give us 6.7%. So she is at the 6.7th percentile. It means she has less shoes than most people. She only has more shoes than 6.7% of the population. Okay, so hopefully that gives you a good idea of what percentile means. Last thing that I do today is look at, well, what if we don't fall at one of these nice spots? This picture is great, but it only gives us certain values. So what if your score does not fall on a whole or half standard deviation? Then your chart can't give you an accurate percentile. Fortunately, we can use these scores in your graphing calculator as an alternative. So example 4 says the top swimmer at FHS swims the 50-meter backstroke on average in 39.7 seconds with standard deviation of 2.3 seconds. Assuming this situation follows a normal distribution, find the probability to the nearest thousandth that she swims her next race between 37 and 44 seconds. Okay, so we can use this idea of this normal curve to figure out how likely you are to fall in a certain range because you've got percents of people in certain ranges. Okay, so since the top swimmer swims on average at 39.7 seconds, this is X bar. Standard deviation is 2.3 seconds. Assuming this situation follows a normal distribution, find the probability to the nearest thousandth that she swims her next race between 37 and 44 seconds. It says sketch your normal curve with the mean at the center. Place 37 and 44 on the graph and shade the area you're trying to find. So you always want to do a sketch. Here's the normal curve. We know the mean's always at the center. So here's X bar. In this case, that's 39.7. I want the probability that this person swims between 37 and 44 seconds. So 37 would be below the mean, 47 would be above, or 44 would be above the mean. I'm looking for this area. Step 2, calculate the z-score for each value round to the nearest thousandth. So the first z-score would be the observed value of 37 minus the mean, 39.7, over the standard deviation, which was what? 2.3. So the z-score for the lower value of 37 is alpha y equals 37 minus 39.7 divided by 2.3. Negative 1 point nearest thousandth, so negative 1.174. Same for the upper z-score. The mean, or the observed score here is 44 minus the mean of 39.7 over the standard deviation of 2.3. And we've got 44 minus 39.7 divided by a standard deviation of 2.3, 1.870. So the second z-score is 1.870. So remember that what that does is it just normalizes it to the z-score with a mean of 0 and a standard deviation of 1. So the same picture, now I could use the chart, except those values aren't on the chart. The chart only gives me nice numbers like 1, negative 1, 0.5. These are too weird. So here's where the calculator comes in. You can use your graphing calculator to determine the percentage of values that fall within the z-scores you calculated in step 2. This is the same as finding the probability that you're in that range. So here's what you got to do. You got to go to, whether you have a new calculator or old calculator, and I'll show you both, you got to go to second vars, and you want to normal distributions. So DISTR talk about distributions, and these are things you'd learn if you took AP Stats. All we're using this year is 2, normal CDF. So the lower, in this case, is the lower z-score. And the lower z-score was negative 1.174. The upper z-score was 1.870. Mean is 0, standard deviation is 1, because that's what it always is. So that's another way that they show mean. It's called mu, but that's mean, standard deviation. That's always going to be 0, 1 for now, because we're normalizing it with z-scores. And I get 0.849, so the probability would be about 0.849, about an 85% chance. Okay, so the newer calculator, you always just put your lower value that you shaded, negative 1.174 in this case, your upper value, 1.870. Again, for now, the mean, so again, that's the same as mean. Mean is always 0, standard deviation is always 1, because that's what it is on the normal curve. And we got 0.84906, which is about equal to 0.849. Now let me just show you quick. If you have an old calculator, when you do second distribution, so second vars, there's still a normal CDF, but it doesn't specifically tell you what to do. You have to type in the lower value, so negative 1.174, then put a comma, the upper value, 1.870, another comma, the mean, 0, another comma, standard deviation of 1, and you get the exact same answer. Okay, so if you have an old calculator, that's how you do it. All right, so there's our probability that this person swims the backstroke between 37 and 44 seconds. Pretty good chance. All right, let's do just a couple more and then we'll be done. Using the same mean and standard deviation of the previous example, so we still have a mean of 39.7 seconds and a standard deviation of 2.3 seconds. Find the probability to the nearest thousandth that the swimmer's time is more than 45 seconds. So we'll draw a picture. mean's in the center, 39.7. So if I want to be more than 45 seconds, I'm looking over here. So the difference here is I've only got one z-score to calculate, 45. So observed minus the mean over the standard deviation. And I can do alpha y equals 45 minus 39.7 divided by a standard deviation of 2.3. Z-score is 2.304. Okay, so on the normal curve, this would be 0. This would be 2.304. Okay, so I'm going to go second bars again. And I'm going to do normal CDF. My lower value is 2.304. But for the upper value, I want to go right forever. So what's forever in math? Infinity. So technically, the upper z-score is infinity, but I can't type in infinity. So what I do is I use a number really close to infinity. 1 times 10 to the 99th power. That's a huge number. That's 1 with 99 zeros. So that can technically kind of mean positive infinity. And then you always put the mean, which is always 0 if I'm using z-scores, with a standard deviation of 1. Okay, so I'm going to go to second distribution again. Normal CDF. My lower is 2.304. My upper is 1 times 10 to the 99th power. The mean of 0, standard deviation of 1. And what this is doing is it's taking that picture. Keep in mind what this is doing. It's taking this picture and it's calculating the area under the curve. It's kind of doing some calculus to calculate the area under the curve between a certain spot and another certain spot. Okay, so what you're really doing is using that picture. Your calculator can calculate the percent underneath there. 0.0106. So that's only about a 0.011. It's about a 1.1% chance she's going to swim that slow, because this is slow values if I'm higher. Okay. All right, number 6. Using the same mean and standard deviations from the previous 2 examples, so still mean of 39.7 with a standard deviation of 2.3. Find the probability in nearest thousandth that the swimmer's time is less than 39 seconds. Again, for every question on your homework, I want you to draw a picture. 39.7, here's 39. I want to be less than that. So I would expect this to be around 50%. That's pretty close to the middle. But find your z-score. So 39 minus 39.7 all over 2.3. .39 minus 39.7. Oh, getting a little ahead of myself. Divided by 2.3. Negative 0.304. Okay, so then I go back to second vars again. I'm going to do normal CDF, and this is the work you got to show. You've got to show normal CDF. This time my lower is negative infinity. So when your lower is negative infinity, what do you think you're going to use? Well, the same idea with a negative. Use -1 times 10 to the 99th. Okay, so that's going to go here. -1 times 10 to the 99th. Upper is negative 0.304. Mean is 0. Standard deviation is 1. So second distribution, normal CDF. My lower is -1 times 10 to the 99th. Going up to -0.304. Mean of 0, standard deviation of 1, as always, 0.381. So it's really not that close to 50%, 38.1%. I guess I'm further below the mean than I realized. Okay, any questions? All right, let's do this last one. Put it all together. The mean score on the ACT is 20.8 with a standard deviation of 4.8. Scores on the ACT follow a normal distribution. What percentile did a person who scored at 27 fall at? First step is always draw a picture. What's going to go in the middle? 20.8. We're looking for the person who scored a 27. And what am I going to shade if I want to know percentile? Well, what phrase are you supposed to think of with percentile? Percents at or below. That's why I told you at or below is important to remember. So go to 27 and shade everything at or below. That's what I'm trying to find. So now this turns out to be a normal type problem. Find your z-score. So observed minus the mean over the standard deviation. Let's see what that comes out to be. 27 minus 20.8 divided by a standard deviation of 4.8 gets me 1.292. Then I go to normal CDF. This is giving me percents. What's my lower? -1 times 10 to the 99th. What's my upper? 1.292, comma 0, comma 1. So that's good. This is 1.292, comma 0, comma 1. Normal CDF gives me 0.90182. So if I wanted to know what percentile, make it into a percent, it's about the 90.2nd percentile, which means this person scored better than about 90% of the people taking the test, which is a great score. All right, so once you get the hang of this, these questions tend to be pretty easy for people. So hopefully that made sense to you. Give the homework a shot, and if you run into any troubles, send me a message. Good luck.